this, and I'll be posting it to YouTube afterwards. So yeah, if you want to watch back over this, get some review, you'll be able to do so. So first thing, and I'm going to go through these somewhat quickly, and if you do have any questions, again, feel free to stop me and I can go over any of these topics in a little bit more depth. So first, let's see. Yeah, I might take attendance while I'm doing this presentation as well. I just have a script that automatically runs and checks where everyone is. So it'll just happen. You won't know about it. But yeah, typically it'll be when you're in the groups. But I might also do it during these because technically this is still part of the lab time. Okay. So the first thing we're going to do is just converting binary to decimal. So let's say we have this number here and we want to convert it to decimal. So this is in binary. So what you want to do is you want to figure out what each place value has. So like in decimal, you have the ones place, the tens place, the hundreds place, and so on, right? It just multiplies by 10 every time. With binary, you start off with 1. So this is the ones place, and then you multiply it by 2 every time. So this is the twos place and the fours place, right? And so we see we have a 1 in the twos place, 1 in the fours place. So this is equal to 4 plus 2, which is 6. So we know that 110 is 6 in base 10. And this subscript here just means what base it is. So 110 in binary is 6 in base 10. All right, any questions on this? All right. Okay. So now do the same thing in reverse. It's a little bit more complicated because you have to figure out what things are going in different places. Let's say we take a look at the number 104. So what you want to do is you want to find the largest power of 2 that fits into this number. So you have 1, 2, 4, 8, 16, 32, 64, 128, right? And this one's obviously too big. So the first one that can fit inside is 64. So we know we have 164 inside of 104. So we can go ahead and subtract that out. That'll just be 40. All right, so then we go down to 32. We see 32 fits into 40. So we can go ahead and subtract that out, put a check mark here. So that'll be 8. All right, we look at 16. We don't have, 16 doesn't fit in there, right? Or 128 doesn't fit, and 16 also doesn't fit now. So we go back to the next one. 8 does fit, right? So then we can subtract 8, and now we're at 0, so that means we're done. And so everything else is not going to be in there. And then if we sort of flip this on its side like this way, we can see that, okay, for 128 it'll be 0, for 64 it'll be 1, for 32 it'll be 1, 16 it'll be 0, 8 it'll be 1, 4, 2, and 1. And there you go. That'll be 104 in binary. Any questions on that? I'll get to the positive or negative. For when it's just asking like what's the number blah in binary and it doesn't really talk about negatives, you just need to get the number represented. And someone asked, do you need the leading 0? In this question, not really. But you will pretty quickly learn that it's very, very important in most architecture related things for the number of bits to be very exact. If the problem says use 8-bit binary numbers, your answer needs to be in 8 bits. If it's just saying, okay, well, what's this number in binary, and it doesn't really specify that, you can just write it out. So this would be correct, this would be correct, or you could just remove both zeros. For this problem, it doesn't really matter. But yeah, I'll get into the negative and 2's complement and all of that a little bit later. See someone else typing a question, so I'm going to go ahead and wait for that. Yeah, well, I mean, so the thing about binary is that it's there's no difference to it and how it works in comparison to what you might call normal numbers, base 10 numbers, right? Is the number 0, 396 the same thing as 396 or the same thing as 0, 0, 396? It's just zeros at the beginning, right? If you think about it, all you're saying is that there's 0 128s in this number, or 0 256, or 0 512s. You're adding 0 every single time you put a 0 in front, so it doesn't really change anything. That's not necessarily true when you get into 2's complement, but for just positive binary numbers, that works fine. Any other questions on this before I move on? And we'll go ahead and start getting into binary addition and then 2's complement, which are the more important things and more significant things I want to cover. All right, let's go ahead and clear that. Okay, so now let's get into addition. And as with a lot of things when you're dealing with binary for the first time, there's really no difference from how it works in decimal. When you're going to add two numbers in binary, you just do the normal addition, except instead of carrying over when you get to 10, you carry over when you get to 2. So let's see here. Let's look at that plus that. Right? So this right here is 5 because that's the 4's place and the 1's place. Right? And this is the 2's place and the 1's place. It's 3. And so we know that the result we should get is 8, which, if you quickly do the conversion, is 100. And this is something I recommend you do yourself whenever you're working on these problems. Convert the numbers to decimal, and then just do the math normally, and then convert the answer. To solve the problem, you'll have to show your work in binary, but you can check your answer this way, right? I know that this is what the answer should be, so if I make any mistakes while doing the binary addition, I'll know where to correct myself. So here, we'll do 1 plus 1, that's 2. But in binary, we represent 2 with a 1, 0 like this, right? Well, here, we had to use up this place, so instead, I'll go ahead and carry that over. Right, so 1 plus 1 is 2, but 2 is 1, 0, and so you end up with a carry. You end up having to carry over to the next bit. Then you can do 1 plus 0 plus 1, that's again 2, so there'll be a 0 here and a 1 here. 1 plus 1 plus 0 is 2, so we put a 0 in the sum place, and then carry 1 over, and then 1 plus 0 plus 0 is 1. That pretty much, or that doesn't cover all the different topics, so I'll go ahead and just do another quick one. Let's say we're doing 7 plus 3. So here we'll do 1 plus 1, that is 2. So we would put this, but we can only fill in this spot right here when we're doing an addition for a single column. So instead we're going to take this one and bring it up here. 1 plus 1 plus 1 is 3, which is 1, 1, right? But we'll bring this one up here. 1 plus 1 plus 0 is 2, which is this. But we can't put that there. We'll bring it up here. But then 1 plus 0 plus 0 is still this. And this is in fact 10. So 7 plus 3 is in fact 10. Any questions on this? All right. So now we'll go ahead and get into 2's complement. And I definitely want to spend the most amount of time on 2's complement because it's quite important to understand how it works. And for pretty much the rest of the semester, we're just going to assume that you know how it works. And, if you don't, it's going to be quite a bit more difficult. So the idea behind 2's complement is that most of any sort of operations you're going to do on the number just work magically, right? It's a negative number that you can just do operations with, and the result just looks right. So let's see what I'm talking about with that. So let's say we're going to do something like 5 minus 3. Okay. So in this class, you want to just pretend you don't know how to do subtraction. Subtraction doesn't exist because we can just add negative numbers. So if we're doing 5 minus 3, really we want to be doing 5 plus negative 3, right? So we'll take the binary number for 5, we'll take the binary number for negative 3, and then we'll just do binary addition together, and we should get 2, right? Because 5 minus 3 is 2. So let's just do this in 4-bit binary, and this is where the bit length matters absolutely. Whenever you're dealing with 2's complement, you need to know the number of bits, and you need to the result always needs to be that number of bits. If there's an extra carry out, it gets ignored. So we look at 5. This is going to be 5 in binary. Then we can just start off with 3, and then we'll figure out how to get -3 from that. And to do that, we'll use the 2's complement algorithm. And the 2's complement algorithm is essentially, you can take a number x and then turn it into -x, right? And if your number you started off with was -x or something, and you make it negative, well, then you'll end up with positive. So the 2's complement algorithm allows you to convert between positive and negative numbers. It doesn't always produce a negative number or a positive number. If you start with a positive number, it'll give you a negative number. If you start off with a negative number, it'll give you a positive number. So keep that in mind. You can't just apply 2's complement because you want a negative version. You have to think about, okay, what am I starting with, and what do you want? Here we're starting off with 3, right? This is 3 in binary, and now we want to get the representation for -3. So how do we do that? As you hopefully learned in class, you invert all of the bits, and then you add 1. So you invert all of the bits, and then you add 1. And don't forget to do the add 1. If you only do the inversion, you get 1's complement, which doesn't have as nice properties as 2's complement does. But if you do that extra 1, you get 2's complement, which is ultimately what we want. So we can go ahead and just do normal binary addition. And when I say +1, I mean literally plus the number 1. So you can just set it up like this, and then just do normal binary addition. 0 + 1 is 1, 0 + 0 is 0, 1 + 0 is 1, 1 + 0 is 1, right? So this right here is -3 in 4-bit 2's complement binary. This is not the number, like if we converted it, that's 8, 4, 2, and 1. So this would be 13, right? In 4-bit 2's complement binary, this is not 13, it's -3. And it's always -3 in 2's complement binary. Because if we also said that it could be 13, then we're calling this number here 2 different things, which doesn't really work. It needs to just be one thing. So according to what we computed with 2's complement, this is -3, right? And so according to this right here, if we add these 2 together, the result should just be 2. And we can go ahead and work through that. So 1 + 1 is 0 with a carry of 1. And 1 + 0 + 0 is 1. 1 + 1 is 0 with a carry of 1. 1 + 1 is 0 with a carry of 1. But again, keep in mind that we want to stay with 4-bit binary. If there's an extra carry out, we're just going to ignore it. And we can see here that this is in fact 2. And that just worked. You didn't have to do any special rules for subtraction, and you definitely do not want to do subtraction because we don't know how it works. We're going to pretend as though subtraction doesn't exist. Any questions on this? I'll go ahead and do another example of it because 2's complement is important to understand. All right. So now let's see, 5 - 7. Or actually, we'll do -5 - 3. Yeah, sure. So here, really what we have, and you always want to sort of do this conversion either in your head or actually write it out just to make sure. But we're taking the number -5 and we're adding it to the number -3. So now we need to figure out how to write -5, and we need to figure out how to write -3. And for this one, let's say we're going to use 6-bit 2's complement. So for 5, pretty much the easiest way to figure out the negative version of a number is just start off with the positive version and then apply 2's complement to it. So 5 is going to be this, and 3 is going to be this. So now we go ahead and apply 2's complement to each. So we'll go ahead and invert all of the bits, and then we'll go ahead and add 1, and that'll be easy. There. Then we'll invert these, then add 1. So again, this right here is 5. This right here is -5 now. And just to point it out, if we take -5, right, we invert, and then we add 1, we get back 5, right? So we know that this has to be -5 because when we take -5, we end up with 5, right? So the 2's complement algorithm is what you're going to use to convert. A little bit of the confusion, there's a little bit of confusion that happens here because the number system is also called 2's complement. So you've got the 2's complement number system, and you've got the 2's complement algorithm. The algorithm, again, is used to convert between positive and negative. The 2's complement number system just tells you that you can interpret this number as a negative number. So 6-bit 2's complement says, okay, this could be positive, could be negative. But what you can actually do with 2's complement is look at that largest bit here, and it's a 1, so you know that this number is negative. It doesn't mean this right here is not -3 because you have a -3. That's not how 2's complement works. You know it's negative, but you can't just read the number like that. What you have to do is you have to do the conversion. So invert, add 1, so now you know that this is -5. Okay, so now we can go ahead and do that addition. So we have -5 and -3. We'll go ahead and add those together. So we have 1, 1, 1, 0, 1, 1 plus 1, 1, 1, 0, 1. So here we have 1 plus 1, that's 0 with a carry of 1. 1 plus 1 plus 0, 0, carry a 1. 1 plus 0 plus 1, 0, carry a 1. 1 plus 1 plus 1 is 1, carry a 1. 1 plus 1 plus 1 is 1, carry a 1. 1 plus 1 is 1, carry a 1. And then this just disappears because we're only working with 6 bits. And so now you might say, okay, well, this is the 1s, 2s, 4s, 8, 16s, and 32s place. So this number right here is 46, right? Well, no, right? Because it's 6-bit 2's complement. So you can look at this most significant bit. It's a 1, which means that this is actually a negative number, right? And let's say initially, assuming that you can't just read 2's complement binary right off the bat, it usually takes a little bit of time to get used to reading 2's complement. What we're going to do is just apply 2's complement to see what the positive version of this is, right? We know this is negative, and we want to get the positive version so we know how to read it. So we can go ahead and invert, then add 1, and we'll get 0, 0, 1, 0, 0, 0. And if we do this conversion, we see this is 8, which means that this right here is -8. And, you know, -5 minus 3 is in fact -8. So we know that the answer is correct. Any questions on this? All right. So let's see here. I do see someone typing a question, so I'll go ahead and wait for that. So question is, what's the reason for choosing 6-bit? I just chose it because I knew that it would be enough bits to represent the numbers that I'm trying to manipulate here. For the most part, you'll just be given the number of bits that you should be using. And it's just important that you do that. If for a more technical explanation, if I take the number 5 and I only write it in 3 bits, and then I try to apply 2's complement to get -5 in 3 bits, yeah. Someone had asked this in the chat, I think yesterday during lecture, and a way that you can think about it is, let's say you have a 2-bit computer. So it stores 2-bit binary numbers and then does operations on them. So let's say you start with 2 plus 3, right? So this is 2 and 3. And you do that addition. So 0 plus 1. So 0 plus 1 is 1. And then 1 plus 1 is 0 with a carry of 1. Okay, so now you have a 3-digit number. So that means your computer needs to be able to handle 3-digit additions, right? So let's say we're doing 5 plus 3 now. So 1 plus 1 is 0, carry a 1, 0. Oh, now you suddenly end up with a 4-bit number, right? And if you continuously have to take into account the extra carry out, you're just going to constantly be adding more and more and more and more bits to your numbers. And suddenly your computer has to handle infinite length numbers. So, and that's obviously not possible. So what the solution is they say, okay, we're going to ignore the carry out, the final carry for the addition. We're just going to ignore it, and we'll say this is the result. This is exactly why you get integer overflows while you're programming. If you suddenly go too big, and that upper limit is the highest possible 32-bit 2's complement number. If you actually look at what the int max is in like Java or something, you'll see that it is the largest 32-bit 2's complement number that you can write in binary. And then if you add anything more, right, like if we're looking at just 4-bit 2's complement, and let's say we look at this number here, this is 7. If I add 1, you get 0, 1, 0, 0, 0, which is actually a negative number. So that's why it sort of wraps around to negative, is you've just sort of taken some of the numbers and put it on the bottom. With 2's complement, it doesn't matter whether the number is positive or negative. And so someone asked, so does this only apply to subtraction and not addition? It applies when you're doing 2's complement, and you want to just pretend as though you've never known what subtraction is. Subtraction doesn't exist. You just have positive and negative numbers, and you can add them together. And if you think about it like that, it'll help you not make little mistakes that end up costing you points. All right, any other questions on 2's complement? And would anyone like for me to go over another example? All right, yeah, we'll go ahead and do one more example. Let's see here. We'll go ahead and do 2 minus 6. Okay, so 2 minus 6, again, subtraction, what is that? I don't know. We can't do subtraction, so we got to convert it into an addition problem, and now we can do it. There is a minimum number of bits that you need to represent certain numbers in 2's complement. So for -6, if we write the number 6 like this, we at least need, right, this is the smallest way we can write the number 6. It's 3 bits, but we can't actually represent -6 with 3 bits, because if we apply 2's because actually if we look here in 3 bits, this is a negative number, right? It's not the number 6, so we can't actually represent 6 in 3-bit 2's complement. We actually need at least one more bit. So, and anytime you come across a problem, the number of bits is going to be large enough. But if you are doing this on your own or something and you want to choose a large enough number of bits, take the largest number, write it out just like how you would normally write it out without any leading zeros, and then you at least have to put one extra 0 in front, because otherwise you won't have enough room to represent numbers. But typically, just look at how many bits it tells you to use and just use that. Don't put anything extra in front of that when you're just given a question like that. Okay, so here, let's see. I should be able to use 4-bit. So 2, we can represent with like that. So 4-bit 2's comp. So 2 is this. 6 is this. So 2, we want +2, right? Because we're doing +2 plus -6. This right here is +2, so we don't have to do anything to it. This right here is 6, it's +6. We want -6, so we have to go ahead and do the conversion. So invert everything, add 1, and we get this number here. Right? So now we can just go ahead and do the addition. So 0, 0, 1, 0, plus 1, 0, 1, 0, 0 plus 0 is 0, 1 plus 1 is 0 with a carry of 1, 1 plus 0 plus 0 is 1, 0 plus 1 is 1. All right, so we end up with this as our answer. We want to figure out if our answer is right. So 2 minus 6 should be -4, right? So this hopefully is -4. We can, if we look at it, we look at the largest, the leftmost bit, we see that it's a 1, which means that the number is negative. So we can go ahead and apply 2's complement to see what the positive version is. So we'll go ahead and invert and then add 1. And we can see that this is in fact 4, which means this right here is -4. And we got the right answer. Any other questions on this? And just to answer an old question that I didn't see. So someone asked about question 4 on the number systems practice once you get to that. For number 4, it's just saying do positive unsigned binary. So whenever it's in 2's complement, the number of bits needs to be fixed. Whenever it's unsigned and we're just like sort of asking to add 2 binary numbers and they may or may not be negative or you can assume that they're positive like in number 4. And so that you would just write however many bits you need. If you need to include the carry, you'll go ahead and do that. But it's pretty much only whenever you're doing 2's complement that you'll pay attention to the number of bits. Okay. Yeah, so whenever you see the term signed 6-bit integer, it typically means 6-bit 2's complement, but there's also signed magnitude 6-bit integers and 1's complement 6-bit integers. So typically we'll say 6-bit 2's complement binary number. But yes, that is a type of signed binary number. And yes, whenever you're dealing with the 2's complement number, like let's say I give you this number here, and I say this is a 4-bit 2's complement number. What you can do is you can look at this first digit here. It's a 0, so that means this is a positive number. And then you can just read it, and it's 2. So you know that this is the number 2 in 4-bit 2's complement. But if it did have a 1 in front, so like if there was a 1 right here, then this would not be 2, this would be -6. I believe. Yeah. No, the number systems practice is not graded. It's meant for you to be able to practice these on your own. And then we'll come back, like you'll spend about half an hour on these. During that time, you can go ahead and ask questions to either your group members or to us if you need. And then we'll reconvene for a second review for tables and Boolean functions. And I'll actually go over any particular questions from the number systems practice that anyone wants me to go over. I'll go ahead and let, I can see someone's typing a question, so I'll go ahead and let them do that. Really quickly, there's also conversion from hexadecimal to binary that I forgot. So let's say I take the number 3D in hexadecimal. So all you need to do here to convert from hex to binary, this is base 16, and if you want binary, all you need to do is take every single individual bit and every single individual digit in the hexadecimal number and convert it to a 4-bit binary number. So 3 is 0011. D is, let's see, is 13, or it represents 13 in this place. And so we can go ahead and write 13 like this, and then you just stick these together, right? So you'll just move these close to each other, and that is 3D converted to binary. So you just do those individual 4 bits. Number 9 from the practice, that's just a fact you need to know. If you don't know it, I'll go over it later. Let's see. So 10, it says use 8-bit unless it's already in binary. Yeah, so for A and C, you'll convert those into 8-bit binary numbers in 2's complement. But for B and D, you just leave that alone. You just leave it to the 4 bits. Okay. I think that's pretty much all I wanted to cover, especially that two's complement. So I'll go ahead and let you all go into your individual group. So what you want to do is you want to join the voice channel for your group. You should have access to only one, so that shouldn't be too difficult. If for some reason you don't have a group, let me know. But yeah, go ahead and join that, work on the number systems practice, and then I'll make an announcement. If you have any questions or you want to call over a TA specifically, inside of your group text channel, do @TA or something. So that'll call us over, let us know what group you're in. We might join your voice chat. We might just respond by text, whatever is most convenient. Feel free to do video sharing between yourselves within the groups. You should have the permissions to do so. If you don't, let me know. Yeah, go ahead and work on that. And I'll send out another announcement later for when we do the second review.